Hello again, class. I am excited to talk to you today about metallic bonds and metallic compounds. So, you might have heard from a historian about the Stone Age, and then eventually, as we study about mankind and different peoples and different places, they eventually get to what they call the Bronze Age. Why was this such a difference in the history of people? Well, what happened was early people discovered that they could mix metals. Now, they knew about copper before this time. We'll look at copper on the periodic table. Right here, it's number 29, and it is a metal, right? They had copper, but copper was soft, and it didn't really do them a lot of good. But somebody figured out that they could mix some copper and some tin, which is number 50. Right there. So they mixed together some copper and some tin, and what they got was bronze. And bronze had different properties because it mixed these two metals together. And this is what we call a metal alloy when you mix two metals together, and they have better qualities, perhaps, or maybe worse, than what they were alone. Bronze changed the world because suddenly people had tools that were stronger and that held up to more difficulty. So you could make tools, you could make weapons, they were soft enough that they could form them, but strong enough to hold up to wear. And so this changed the world, and we have the Bronze Age. Eventually, people got around to something called, do you know what the next age is? It's the Iron Age. And the Iron Age was when they figured out that they could work with iron, which right here. Sorry, it takes me a minute to find things on the periodic table. So iron right here by itself was harder, and because it was harder, they couldn't form it very well. But when they figured out how to do that, then we entered a new age with even better tools. But the Bronze Age, which started about 3000 BC, maybe even further back, really changed the nature of everything that could be done. Farming could be done because they had better tools to plow fields, and societies could advance, and things changed dramatically during the Bronze Age. So what is it that makes those bonds in bronze happen? What makes them behave like they did to make things better for us? Well, let's talk a little bit about metallic bonds. You're going to learn today about why metals behave like they do. We learned about ionic compounds last week. You might notice that we have cations drawn in red. So in an ionic compound, you have this grid or lattice or crystal structure where your cations and your anions all are joined together one by one, and you go every other one, cation, anion, cation, anion. Now this is the simplest grid. There are other formations and structures of how these join together, but you get the basic idea of what we're talking about here. And it forms a crystal structure, but as we talked about, brittle. How is it different in a metal? We know that metals form, or maybe you don't know, but metals do form crystal structures as well, or lattice structures, really. They're not really crystals because they are not as brittle. And they're not see-through like you might get a beautiful crystal as you picture in your mind, but they're still forming structures. If you look at a metallic compound, all of these metals here will give up some electrons, and so we have positive ions. And the positive ions form a structure. So you see what right here, these cations are forming the same kind of lattice structure that we talked about before, but everything in that lattice structure is a positive ion. And then what we have floating around there is these electrons that I've drawn in light blue. So we have these little negative electrons floating all around. And what happens is all these outer valence electrons of the metal atoms are basically almost in what we call a soup around the lattice structure of the positive ions. And so because all of those electrons are not very tightly bound to any individual nucleus, they kind of can move freely. And that gives everything the properties that we like in metals. It gives it the property of conducting electricity because those electrons can move, and conducting heat because those electrons can move. Most metals are malleable, meaning we can mush them around. They are generally gray. They are a little bit shiny, and they are not brittle like the ionic compounds are. It would be a really good idea for you now to start a table, if you haven't already, or finish a table in your notebooks. You should have a column for covalent compounds, a column for ionic compounds, and a column for metallic compounds. And you should make some rows and compare these different qualities of these compounds so that you can tell the difference between what the different ones are and what they do. When we get these structures that I have drawn here for metals, there are two different types of lattice structures that we want to talk about. And remember, I talked to you about alloys like bronze. Let's look at one of those first. So there are two different alloys or types of alloys. If I were to say that these are still cations, but let's say this is copper, like I was talking about with bronze. If we were also going to look at a cation of tin, it is not a whole lot different in size. So as things are really close to the same size in metals and you mix them together, you might just replace, a couple random ions with these ones. And this forms an alloy. You notice that the structure is very similar to what it was before. Now, why are metals malleable? Well, because in this structure, you can, if you pushed some of this material from the side, all of these bonds could just slide over one. You could take this whole block and you could move it over one, and it would still line up in the same structure. And that's why metals are malleable. You can just squish them. They don't break because those bonds, it's the electrons are floating all around. Those are all cations. You can move them and it doesn't mess up whether the positive is hooked to the negative, to the positive, the negative, like it would in an ionic compound. So you can squish it and it'll move. So we can form an alloy where you just replace a few of those atoms with a different type of atom, and it gives it some other properties, and it's awesome. This is called, as I said before, this is called a substitutional alloy, where you just replace some of the ions with different ions, or some of the atoms with a different material, and you get new qualities. There's a different kind of alloy while you mix them together, and that's when the sizes of the atoms are quite a bit different. Let's say this is iron now. What if I want to mix some iron with some, for example, copper? Do you know what you get when you mix iron and, oh, I didn't mean copper. Wow. Carbon. I knew it started with a C. If you want to mix iron and carbon, you get something that you might recognize. So we have iron right here, and copper is, or carbon, again, carbon up here. Carbon, iron. We mix carbon and iron together. You might notice that carbon up here is quite a bit smaller atom. So let's draw carbon with a smaller size dot. Let's say carbon's more like this size. If you mix those two together, guess what happens? You get something that we call an interstitial alloy, where you get like little carbon atoms. They can just mix inside those bigger atoms. And that mixing makes also some different properties happen. And it actually changes the way things are malleable. And what happens is it actually makes it stiffer, because if you try and push now, like I was talking about before, and you want to push this structure over, some of those little atoms are kind of in the way of the bigger ones. And so it makes it not push as much. So you get more stiffness in this kind of a metal that is an interstitial alloy than in a substitutional alloy. Let me write this down. It's an interstitial alloy. So I just want you to understand that we have these two different types of alloys, but both are mixtures of different kinds of metal together. And they still have all those properties of metal. What other properties of metal do you know? Like if you think of every metal you know, what are they like? Well, they're all pretty much solids at room temperature, you might have noticed, except for one huge exception, and that is mercury. If you probably haven't played with mercury. We used to do that when I was a kid, and then we found out how toxic it is. But if you ever get the chance, don't push it with your fingers, okay? But mercury is liquid at room temperature, and it behaves really neat. So watch a video if you can't really play with it yourself. But it is the one exception. All the rest of the metals are solids at room temperature. Hope you have some fun this week learning more about how these metallic bonds work. Dig in deep, and I hope you understand it. Thanks so much.